Welcome to the subject electromagnetic waves and transmission lines. In this session, we shall be discussing the Maxwell's equations, not the total Maxwell's equations, two Maxwell's equations which are relevant for magnetostatics. Well, you know, totally there are four Maxwell's equations, two for electric domain and two for magnetic domain. In this session, we shall be discussing two Maxwell's equations, the two which are meant for static magnetic fields, which means Maxwell's two equations for magnetostatic fields are for magnetostatics. Even though the Maxwell's equations are actually meant for time varying fields, first we should try to understand how the equations will look in its static form for static electric fields, static magnetic fields. In unit 1, we have seen two Maxwell's equations for electrostatics. In unit 2, in this discussion, we are seeing two Maxwell's equations for magnetostatic fields. In addition to that, we also have one more topic, magnetic potentials. Like we have electric potential in unit 1, we have magnetic potentials in unit 2. I am using the word potentials, plural, whereas in first unit I said singular, electric potential. Here I am saying unit 2, magnetic potentials, means there are more than one potential in magnetostatics. What are they? Why there are two magnetic potentials unlike single electric potential? That will be discussed in this session. Now, the first topic is Maxwell's two equations for magnetostatic fields. Starting with the first one, we know the closed contour surface integral of magnetic flux density does not exist. Mathematically 0 means it does not exist. What does not exist? The integral of magnetic flux density over a closed surface is 0. What is the reason? The reason is simple and straightforward. Unlike electric lines of force, magnetic lines of force does not diverge. Electric lines of force diverge. Magnetic lines of force do not diverge. They form a closed loop, which we have seen in the earlier discussions. So the mathematical representation is integral B dot ds closed surface integral is equal to 0. Now this is the starting point. Now on applying divergence theorem, this expression will become equal to this expression. Now the question is, why do you apply only divergence theorem? Why not Green's theorem? Why not Stokes theorem? The reason is, divergence theorem establishes a relationship between a closed surface and a volume. See, this is a surface, a sheet. It's an open surface. This is a closed surface. This is surface but which is closed. Inside the closed surface, you have some volume. So that's why we are making an equivalent for this closed surface with this volume. And divergence theorem relates a closed surface with a volume. Then why do you take closed surface? Because here in this integral, you have a surface which is closed, a closed surface integral. Now, what divergence theorem says? The closed surface integral of any vector, let us say I take some vector C bar, some randomly I am taking some alphabet, C bar, because it is surface integral I am taking ds, can be equivalently written as, means this entire thing can be equivalently written as the volume integral of divergence of that vector. C bar is a vector dv, because it is volume integral, I write here dv. I repeat once again, the closed surface integral of any vector, closed surface integral, can be equivalently written as the volume integral of divergence of that vector. So in place of C bar, we have here B bar. So this closed surface integral of B bar is equal to volume integral of divergence of this vector. We have divergence here. That is the reason it is also called as Gauss divergence theorem. You can also say applying Gauss divergence theorem. So this entire term can be equivalently written as this. So, but what is this equal to? 0. So this entire thing should be equal to 0. That's what I have written here. Volume integral of divergence of B bar is equal to 0. Now, if this left hand side is equal to 0, then there are two possibilities. Either the volume over which you are integrating, it should be 0, or divergence of this vector, means you are calculating divergence from vector, in this case b bar, it should be 0. In either cases you will get 0. But the volume integral of this region is not equal to 0, because you have a finite volume. You have a finite volume. The volume cannot be 0. So what should be 0? Del dot b bar should be equal to 0. That's what's written here. This is one equation. Now, if you want to understand this in a statement form, how do you read it? The divergence of magnetic flux density does not exist. Del dot means divergence. B bar is magnetic flux density. 0 means, mathematically 0 means, physically we say it does not exist. So how do you make a statement? The divergence of magnetic flux density does not exist. This is the first equation. Now going to the second equation, because what are the predominant parameters in second unit? Magnetostatics. 1. Magnetic field. 2. Magnetic flux density. This entire discussion was based on magnetic flux density. What is other parameter? The other one is magnetic field. And there is an important law which we have seen in the previous sessions pertaining to magnetic field. What is that? Ampere's circuital law. And what it says? Integral H dot dl equal to I. I have also given the statement in the previous class. The integral of magnetic field over a closed path, because it is line integral, we say it as path, closed line, closed path, is equal to the current that is enclosed. This was the statement that we discussed. Now this forms the starting point. What we have to do? Apply Stokes theorem. Why Stokes theorem? Because Stokes theorem relates a closed path and open surface. Because this is a screen on which I am writing, this is a two-dimensional screen. It may not be possible to make a distinction between a 3D and 2D, because when I say closed surface, this is how I have to draw. When I say closed path, this is how to draw. But the thing is, if it is a surface which is closed, inside you have volume. If this is a path that is closed, inside you have surface. That you should understand. Because I am representing everything on this screen which is 2D. That you should understand. Previously I have drawn this diagram. It was closed surface. Now I am drawing the same thing. It is closed path. Inside you have surface. So what you have here? Closed line means closed path. You have surface. And Stokes theorem relates surface and closed path. So applying Stokes theorem, what Stokes theorem says? The integral of any vector, I am taking z, some vector z. The integral of any vector over a closed path, L means length, it's a line, path, dl, can be equivalent written as the surface integral of curl of that vector. Z bar is a vector. The surface integral, so I write ds. In place of z, we have h bar. So how do you get here? Surface integral of curl of that vector. This entire thing is equivalent for this, but this is equal to I. Here you have. So this will be equal to I. So this thing is equal to I. Now left hand side you have surface integral. Right hand side, first of all, you don't have any integral. If you get an integral, it's better if you get in terms of surface integral, to establish a symmetry in terms of integrals. Simply speaking, a mathematical symmetry, so that we can get more insightful observations. So now, the left side you have surface integral. Can we express this right hand side in terms of surface integral? The answer is yes. How? Like this. Current I is written as integral of current density. What is J bar? We discussed earlier. I is current, J bar is current density. We have seen that earlier. So current is written as integral of current density. Like if you integrate charge density, you get charge. If you integrate flux density, you get flux. If integrate current density, get current. What kind of integral? Surface integral, because amount of current crossing a unit surface area. Now you have symmetry. Left hand side surface integral ds, right hand side surface integral ds. Then del cross h equal to j bar. That's what I have written here. Del cross h equal to j bar. Now how do you make a statement out of this? Del cross means curl, h bar means magnetic field, j bar means electric current density. How do you make a statement? J bar, the electric current density, can be obtained by the curl of magnetic field, or vice versa. You can say like this. The curl of magnetic field will give you electric current density, or in a mathematical sense, the curl of magnetic field must be equal to electric current density. This is how we understand this second Maxwell equation. The next topic is magnetic potentials. In electrostatics, that is in electric domain, there is only one potential, that was V. V was the electric potential. But in magnetostatics, we have potentials, plurality. There are two potentials. One is scalar potential, another is vector potential. Why do you have two potentials in magnetostatics? And why only single electric potential in electrostatics? The answer is like this. See, if you have an electric charge, you will have electric field. Simple and straightforward. If you have electric charge, you will have electric field. Means to have electric field, the electric charge need not move. Just presence of electric charge will give you electric field. But whereas in magnetostatics, to get magnetic field, electric charge should move. That's what we say, isn't it? A current carrying conductor is surrounded by magnetic field. So when do you get magnetic field surrounding this conductor? When current is flowing in this. Current is nothing but flow of electrons. And the direction of magnetic field is by direction of flow of electrons. If flow of electrons is like this, means if the direction of current is like this, then you have magnetic field given by this right hand thumb rule. Thumb indicates direction of current, curly fingers indicates direction of magnetic field. If electrons are going down, magnetic field will be like this. That means magnetic field is due to the flow of charge, and the direction of magnetic field is due to direction of flow of electrons. That means directional component is involved here in this magnetostatics, or in the study of magnetic fields. Directional component is involved means vectorial nature is involved. Means in addition to scalar potential, we also get vectorial potential or vector potential. That's why we have two potentials. This first one is scalar potential. The second one is vector potential. So what is Vm? Vm is scalar magnetic potential. A bar is vector magnetic potential. That's why I have written here bar here on A. And the symbols are also standard. I am not just writing randomly. Already in electrostatics we have electric potential V. Now again if I write here V, it will be confusing. So I am using the subscript Vm. Vm stands for magnetic. V stands for scalar potential. Vm stands for scalar magnetic potential. And A bar is anyhow vector magnetic potential. Now let us try to understand scalar magnetic potential. I am saying Vm is scalar magnetic potential. Just by saying it will not become scalar magnetic potential. It has to satisfy some identities. So we have a powerful identity for scalars. That is, if a quantity is really a scalar, then it must satisfy a condition. Because we are dealing with scalar potential first. I am taking scalar condition. There is an identity for scalars. If I am saying Vm is a scalar magnetic potential, then it has to satisfy this. The curl of gradient of any scalar must be equal to 0. If V is supposed to be a scalar. If I claim that some quantity is a scalar quantity, then it has to satisfy this. What is this? Cross means curl. Nothing is there. Means gradient. Del followed by some parameter. Nothing is there in between. That is gradient. Dot means divergence. Cross means curl. Square means Laplacian. This is gradient operation. This is curl operation. The curl of gradient of any scalar must be equal to 0. Must be equal to 0 if that is a valid scalar. So I am saying Vm is a scalar magnetic potential. So in place of V, take Vm. The equation remains same. Now, you need to substitute in place of del Vm something. What is a something? In unit 1, we have a relation, very famous relation. What is that? E equal to minus del V. This was in unit 1. This was called as gradient relationship in electrostatics. Similarly, in place of electric field, substitute magnetic field, write del minus del. In place of electric potential, write magnetic potential. Just H equal to minus del Vm. That's what I have taken here, H equal to del Vm. In place of del Vm, you have to take, because H is minus del Vm will be equal to minus H. So, substitute in place of del Vm minus H. So, in place of del Vm I have taken minus H. So, del cross minus H equal to 0. But you know, just now we have seen in this discussion, del cross H equal to J bar, isn't it? Del cross H is J bar as per Ampere's circuit law. We have started with Ampere's circuit law. Del cross H is J bar, del cross H is 0. Del cross minus H is 0 means del cross H is 0. This can be written as del cross H bar equal to 0. This thing can be written as. So, one equation says del cross H is 0. Another equation says del cross H is J bar. Left hand side is same, but right hand side is here 0, here J bar. What does it mean? J bar should be equal to 0. That's what I have written here. That is J bar equal to 0. That means this contradiction will be avoided, because here we have right hand side equal to 0, right hand side equal to J bar. Left hand side is same. Minus H bar means if it goes right side, it will become del cross H bar equal to 0. So, to avoid this contradiction, this is as per identity, this is as per Ampere's circuit law. This contradiction will be avoided if J bar equal to 0. That means H bar equal to minus del Vm, because we have started there. H bar can be equal to minus del Vm only for J bar equal to 0. This is a mathematical expression. But what actually it means physically? What does equation says? It says that we are in the discussion of scalar magnetic potential. If you want to use scalar magnetic potential, then J bar have to be 0. That means scalar magnetic potential can be applicable only when J bar is 0. What is J bar? Electric current density. 0 means does not exist. Scalar magnetic potential is applicable only for current density equal to 0, or only when current density does not exist. That is the actual meaning of this discussion. That means scalar magnetic potential, if it has to be used, then current density does not exist. 0 means does not exist. Next, let us go for vector potential. There also does it remain same. Now, if I say A bar is vector magnetic potential, just by saying it will not become vector magnetic potential. It has to be validated. For validation, we have one more identity. This is that identity. If I say some vector is if I say some quantity is vector, then it has to satisfy some identity. What is that? The divergence of curl of that vector should be equal to 0. Now, what I am trying to validate? A bar. So, I have directly taken A bar. Now, if you observe carefully, this equation can be recognized as the equation which we have just now derived. Del dot B bar equal to 0. Here you have del dot, here you have del dot. Here you have 0, here you have 0. B bar. Where do you get this equation? Del dot B bar equal to 0? Here. Del dot B bar equal to 0. This form. Now, on comparing that, here, B bar is equal to del cross A bar, because del dot 0 0. So, B bar is del cross A bar. What does it mean? This is an equation. What does it mean? The magnetic flux density is obtained by the curl of magnetic potential, isn't it? A bar is magnetic vector potential, B bar is magnetic flux density. How do you read this equation? The curl of vector magnetic potential is equal to magnetic flux density. That's the meaning. Now, still we can proceed further. Where did the problem occur in terms of scalar potential? The problem occurred in terms of del cross H equal to J bar. Identity says del cross H is 0, but circuit law says del cross H equal to 0. The contradiction appeared here in the previous case, scalar potential. Now, take the same equation and start here. what happens in this case? Let us see. Del cross H equal to J bar. What is H? We know there is a famous constitutive relationships. Three relations we have in electromagnetics. One is D bar equal to epsilon naught E bar, J bar equal to sigma E bar, B bar equal to mu naught H bar. These are called three constitutive relations in electromagnetics. This is not required for us in this topic. This is also not required. What is pertinent here is B bar equal to mu H bar. What we have here? H bar. So I can write here H bar equal to, H bar is B bar by mu naught. Just rearrange the terms. That's what I have substituted. In place of H bar I have taken B bar by mu naught. So del cross B bar by mu naught equal to J bar. Take this mu naught to the right hand side because mu naught is constant. Permeability of free space 4 pi into 10 power minus 7 is a constant. Then I can write del cross B bar equal to mu naught J bar. Now, is there any necessity for J bar to become 0? Is there any contradiction here in this discussion? No. That means to define vector potential or for the utility of vector magnetic potential, J bar need not be 0. Unlike the case here J bar should be equal to 0. But here there is no need for J bar to be 0. That means vector magnetic potential is applicable. For that, J bar need not be equal to 0. However, for scalar magnetic potential to be applicable, J bar has to be 0. That is the distinction between scalar potential and vector potential in magnetostatics. So, to summarize today's discussion, we have seen Maxwell's two equations for magnetostatic fields. We have seen two potentials for magnetostatics. And this summary comes like this. Del cross B bar. We know what is B bar? B bar is del cross A. So, in place of B bar, substitute del cross A. So, you get del cross A equal to mu naught J. This mu naught J is as it is in the right hand side. There is no change. So how do you understand this? Curl of magnetic potential will give you electric current density because del cross A bar equal to B bar. The double curl operation, that means if you perform curl operation on magnetic potential, once you get magnetic flux density. If you perform twice curl and curl, then you get electric current density. So you get densities in both cases. Be very careful understanding this. Here I am performing curl operation on magnetic potential. Curl operation on magnetic potential. I get magnetic flux density. I am getting a quantity which is density. Magnetic flux density. Single curl operation of magnetic potential gives magnetic flux density. Curl and curl, double curl of operation of the same magnetic potential will give you electric current density. Single curl gives you magnetic flux density, double curl gives you electric current density. So with this we conclude the discussion of magnetic potentials, scalar potential, vector potential and Maxwell's two equations, one written in terms of B bar, another written in terms of H bar.